All right. This morning we have seen a couple of complexity classes. These were all classical complexity classes related to the Turing machine model. So we had the class P and P. First, how do these relate? So you remember, a class is a set of languages. And what are the inclusion relations not known for these two? What would you think? So remember, P is this problems, decision problems that we can solve in polynomial time. And NP are the decision problems for which, if you know the solution, we can verify the solution in polynomial time. Less than equal? Yeah, like this, yes. This is contained, is a subset of this, yes, exactly. But we also have seen another class, bounded error probabilistic polynomial time. And here the relation is the same, right? So here we have probabilities that we could use if we want. Here it's everything deterministic, so we can also do the deterministic things here, but we have the extra power of using probabilities. Actually, this is unknown. We don't know whether they are the same. And here also, but this is kind of the most famous question, one of the most famous questions in computer science. And then we had PP. Remember, here we had bounded error. Here we don't have bounded error, so this is kind of obvious. And here this is kind of, we can just guess the solution. And then we had polynomial space. So the inclusion from here to here is also very obvious. What is the, yes?
What's the relation between NP and BPP?
NP and BPP? We don't know. Also this we don't know. Yeah. It's conjecture that BPP is in NP, but there's no proof. Yes. So maybe it could be that with just probabilistic Turing machines we can solve NP problems, but we don't know. What is the simple argument for this? So this is polynomial time. We can decide whether a word is in the language or not in polynomial time. Here, we can decide whether the word is in the language or not in polynomial space. Why does this hold? What is a simple argument for it?
Because if you only have polynomial time, you can't write down more than polynomial spaces down.
Exactly, yes. Very good. So now, but this is kind of weird, right? Because, so actually it's strictly contained in P-space. But in physics, often time and space are treated on this more or less on the same footing. So why, if we just talk about time, we have something else and we can talk about space? And we will see if we change the notion of causality. I think we'll get to that tomorrow, maybe today already, I don't know. Then we'll see that we can make space to time to something similar than space. We can revisit time. Like space, I can go here and go back and can go here again and go back. But in time, not, right? 1 second or 1 hour in the future, I will pass this moment, but then I cannot go back. But if we change the notion of causality, we can go back and we can reuse kind of space. And you will see some interesting thing that happens here. Okay. But before we go to that, let's talk about quantum computation. To kind of put quantum into this picture, where are the quantum complexity classes in this picture? So this is a very, very short intro. Quantum information. So quantum theory is based on 4 postulates. I think this is the easiest way to see it. So we have postulate 1 defines states and where states live, quantum states. So a so-called pure quantum state is a unit vector. So this means the vector has length 1 in a Hilbert space. So a Hilbert space is just a vector space with the inner product. Okay? It's a complex vector space with inner product. Okay? So let's look at a 2-dimensional vector space, one of the simplest cases. And this is a vector, and it's a quantum state. It represents a quantum state in a 2-dimensional Hilbert space if it is a unit vector. So we have that absolute value of alpha squared plus absolute value of beta squared is 1. Okay. And you know, in linear algebra, or if we talk about vectors, we can always choose a basis and then describe everything in that basis. So what I will introduce now as a basis, which we will use often, is called the computational basis. And the 2 elements in that basis are this, which is, according to this postulate, it's a quantum state, a pure quantum state. It's a vector in a 2-dimensional Hilbert space and has length 1. And the other one is this. And this forms a basis, right? And we denote this actually by this symbol. So this is a notation some of you might have seen, some not. It's called a ket. So I have a line and then a 0, like the bit 0, and then this closing triangle. And this is defined as this vector. And the 1 ket is defined as this vector. Why are they called ket? Because if you take the transpose conjugate of a vector, so let's say I have alpha, beta, and by this dagger symbol, I mean transpose and conjugate. Thanks. I get the conjugate of alpha and the conjugate of beta, but the vector is now like this. Okay, so for the 0 state, the complex conjugate transpose, I will write this like that. Okay, this is called a bra. Right. And the same for 1. Sorry? Oh, yes, of course. Yes, thank you. Thanks. Yes. So, and now you maybe have guessed why we call one bra and the other ket, because if we have some vector like this times a vector like this, actually we often write it just this is a product, right? A vector product. It will give us a number, right? It's a vector like this times a vector like that gives us a number. And we often just will remove one of the lines. So we write this. And this is now a bracket. It's a bracket. And it gives us a scalar product. Okay? It's the inner product of these two vectors. All right, so the quantum state, let's say now in the two-dimensional case, we will now express it using this computational basis. And what we get here is just alpha ket 0 plus beta ket 1. All right, these are so-called pure quantum states, so these are isolated systems. But now we can think of a scenario where we have, as an example, the state 0 or the state 1, but we don't know. So there's someone preparing the state for us, but with probability p, this is prepared, with probability 1 minus p, this is prepared. So how should we now deal with this? And for this, this is called a mixed state. And this example will be, as if with probability p, it's the 0 state. So we actually just write the projector onto the 0 state. So this is a matrix now. Right? This is a vector like this times a vector like this. Plus 1 minus p. And we often use Greek letters to denote such states. Okay. And you can show that mixed states if and only if the trace is 1. So this reflects the fact that the probability sums up to 1. And positive semi-definite and Hermitian. This means we don't have negative probabilities. Okay, so it's so much about states. Now let's talk about composition of states. So this can be seen as the second postulate. Positive semi-definite. The eigenvalues are not negative. Hermitian. It's this. Yes. So if you have now two systems and we want to describe both systems in one expression, we use the tensor product or the Kronecker product. And they will live in the tensor product of the Hilbert spaces. So let's say we have one pure state, just for simplicity. Or, yes, just one pure state in some Hilbert space A. Let's call this system A. And this Hilbert space has some dimension, but I don't specify. And another one in the Hilbert space B, also with some dimension. Then, if the joint both systems, if I describe them together, they live in the Hilbert space A tensor Hilbert space B, and the state is composed by taking the tensor product. Right. And what is a tensor product? So if I have some matrix or vector A, tensor product B, this is, I can now write down A in its single entries, so A11, A12, and so on, A21, and so on, tensor B. And now this symbol, the tensor product, is defined in that way that the tensor product of A and B is just A11 times B, A12 times B, and so on. So I multiply this matrix or vector with every element in the first. So as an example, the zero ket tensor, the zero ket. What is this? So first of all, what is the dimension of the vector? Sorry? 4, yes. And the solution, the vector is? Yes. Okay. And now we look at 3, postulate 3. Therefore, this and one more. Let's call this the evolution. So this postulate will tell us how a quantum system is evolved through time. What are the operations that we can perform on quantum systems? So in the isolated setting, an evolution is described by a unitary operator. A unitary matrix, U. So what does it mean that the matrix is unitary from linear algebra? It means that U dagger, so U complex conjugate transpose U is the identity. And this is the symbol for the identity matrix. So this is 1, 1, 1, 1, 1 in the diagonal, and the rest is 0. So if you have a state, phi, and we can apply a unitary operator to this state, U, and this is done by this, like this. So we have a vector, this is a matrix, so we have the matrix vector product, and we get a vector, and this is the state after the evolution. All right. So why unitary? It will preserve the length. So this is a unit vector, it has length 1. After application of the unitary, we get a vector with the same length. And it preserves in the product. If you have two states and apply the same unitary to both states, the inner product stays the same. As an example, so who of you knows this? Actually, maybe I'm, okay, some people. So an example of a unitary is the Hadamard gate. I call it H. which is defined as the following. So it's 1 over square root 2. And then we have this matrix 1, 1, 1, minus 1. Okay. So this is a unitary that acts on a quantum state of dimension 2. So it's obvious that it's kind of unitary because this matrix time, well, this is the complex conjugate transpose of this is the same thing because there are no, it's a symmetric, it's a Hermitian. And this will give this, which is identity. Okay. So if we talk about mixed states now, how do we apply a unitary on a mixed state? So here I showed you how to apply unitary on a pure state. It's just a matrix vector product. But if you have mixed states instead, how could we do this? So the mixed state, if you write the pure state as a mixed state, like this is a pure state. If you write it as a mixed state, it's just a projector. So this is kind of in this mixed density. It's called also density operator of a pure state is this. So, but if you apply the unitary u, you said you get phi prime. So this is mapped to this. And how is this done? We just apply u on both sides. Right. So if you have a mixed state rho, and we evolve it unitarily with the unitary, then rho is mapped to u, rho, u dagger. Okay. And finally, we talk about measurements. So a measurement is described by a collection of measurement operators. And I will call them M. So we have an indexed set, and every element is called a measurement operator. And they have to satisfy the condition that if we sum over all elements in this set, and take the dagger, the complex conjugate transpose time the matrix, we get the identity. Okay. And now if you have a quantum state and want to measure it with these measurement operators, the probability of observing outcome I, if you measure some state phi, is given by this. And now you see why we have this condition, right? If you sum over all probabilities, you get 1, yes. this is identity. And since state is a unit vector, we have 1. All right. And then also for mixed state, we can also measure mixed state. So this is again, we measure a pure state. Yes?
The conjugate mod scale of the probability of the inner product
Yes?
in that equation. Yeah.
This one?
So, is it a conjugate scale? Mod scale?
This one, yes.
Yes, we did.
Ah,
It's mod square of m times 5. I think that's it.
Mod scale of the inner product.
mod square.
Yes, sir.
No. What,
No, sir.
what do you mean?
No, I think maybe you can write that this is equal to the norm square of m times 5. Because I think they remind that when you have an amplitude, and then probability is the mod square of amplitude.
This? You mean this?
No, sir, in the last equation, I think so.
This one?
Yes, sir. Okay, sir.
I don't understand. So, if the probability of I is given by this expression, now if you sum over all over I, we get this. So,
I think they remind that when you take the usual normalization for state is the sum of the modulus square
Of the arbitraries?
amplitudes.
Of the inner product of two states.
Yeah, so that's a particular case where mi is a projector,
yes.
and then you get that this is equal to the sum of modulus square of 5 scalar product with the basis state.
Yes, sir.
Okay. Okay. So if you have, as an example, if you make a measurement in the computational basis, then the measurement operators, one is this, and the other one is that. Now if you measure some state, with this measurement operator, let's say we want to see what is the probability of measuring 0, then according to this but since M0 is a projector, we have this. Do you mean this? Yes, okay. So it's the modulo square of the ket or the bra 0 times the state. Yes. And this is for that state. That's correct. Yes. So coming back to mixed states, so here I described you how to calculate the probabilities for pure states, for vectors, but if you have such density operators, then the probability of measuring I is given by trace mi rho. Okay. So you see, we recover the same thing if rho is a pure state. Like if rho is a pure state, then we have yeah. M dagger M, yes. Thanks. If it's a pure state, we have this expression, and the trace is cyclic, so we can just move this vector to the left, and we get a number. We don't need the trace anymore. And we recover the expression we had before. All right. One could also talk about what happens after the measurement, what is the state after the measurement, but this we actually don't need, so we will not go into this. All right. So questions on these four postulates, the foundations that we need to talk about quantum computation. We will use these rules throughout the rest of the lecture, so I hope you get familiar. So let's talk now about quantum computing. So we have now the postulates of quantum theory, and we can now build a computer using this, theoretically. All right. So first, note that classical, in the model of the Turing machine, we had the symbols that were written on the tape, and we said we could restrict ourselves to bits, and the start and the space and the empty symbol. So classically, actually, all computation can be done on the bits 0 and 1, and we replace this now by quantum bits, so-called qubits. And we have seen them before. It's the ket0 state and the ket1 state. Okay. And in a quantum computer now, we don't have a transition function like in the, well, we have a transition function, but it's not of the same type as in the Turing machines. But here the operations that we apply are unitary operations. And then at the end, we have to measure something. And then depending on what we get, we can either accept or reject a certain word. So one step to go would be to define just now the analog of the Turing machine, the quantum Turing machine. This has been done, it has been defined, but I think it's not a very nice approach to quantum computing. It gets very complicated and technical very fast. But instead of talking about the quantum Turing machine, I will present you the quantum circuit model. So in a quantum circuit model, we have gates, like in classical circuits. We have AND or NOT gates. In quantum circuits, we also have gates, and we compose them in order to compute some function. And one set of gates is the Hadamard gate that we have seen. It was there on the other board before. I've erased it. The T gate we will need. So this is this operation. So the Hadamard gate is a gate that acts on a single qubit. The T gate as well, it acts on a single qubit. And we also will need the so-called C NOT gate, controlled NOT gate, which will act on 2 qubits. And it's written like this. So, can you read that? The last line? Yeah? Yes? Good. So, what does this do? So, no, first, how do we write down these gates? So, we will draw them with boxes. So, the Hadamard gate, which is draw a box with an H, and then we'll read from left to right. So we can put in, we have seen before that if we put in 0, we computed the operation of a Hadamard on a 0. Oh no, we didn't, but we could do that. What do we get? Yes. 0 plus 1. Yes, 1 over square root 2. 0 ket plus 1. Okay. And the T gate, we also draw it in the same way. So again, we have input, some state. Output is T applied to that state. And then for the C NOT or controlled NOT, it acts on 2 quantum systems, 2 qubits. But actually, we write it like this because you see how it works and it makes sense. And here I have to explain what this last symbol is, the sigma x I've written here. This is just a bit flip. So the action of this gate is that if on the first system I have a 0 state, a ket 0, then on the second system I don't do anything. But if on the first system I have a 1 state, on the second system I flip. Okay? So 0, 0 is mapped to 0, 0. But if I replace here, I put 0, 1, is mapped to 1, 1, exactly. Okay. And actually, we don't need more gates. So there's this famous theorem called the Solovay-Kitaev theorem. And this theorem states that every unitary can be approximated by using a discrete set of universal gates. And if we translate one set of gates to another one, we have a polylogarithmic increase in the size. Or in the length. So these three gates, they're enough to construct any unitary operation that you can think of. Or to approximate, more precisely. It could be that we cannot write. So if you have a unitary operation in mind, a quantum operation that you want to do, it's enough to use these three gates, and you can approximate it arbitrarily well. So that's why this is called the universal set of quantum gates. Okay, so so you see, we talked now about circuits, about gates. We combine gates to construct a circuit. So for instance, we can do this, a Hadamard, and then we can do controlled NOT as an example. And this is a circuit. And we now want to talk about circuits and computing things. But there's a crucial difference between the circuit model, like having a circuit like this, and Turing machines. And what is the main difference between these two?
This has to be reversible?
This has to be reversible, yes. This is one difference, yes. But you can make you can just add more systems and then forget about some parts, and then it's also not reversible anymore. Or a Turing machine, you can also make a Turing machine reversible. You don't lose in the properties of the Turing machine stay the same, even if you make all operations reversible. You can make the transition function reversible. But there's another crucial difference between circuits and Turing machines. Yes?
Turing machines can have arbitrary input sizes?
Yes, exactly. So a Turing machine, you can give an input that has any length. But here, like in this example, we are restricted to 3 qubits. So if we talk about deciding a language, we would like to pose the same question, decision problem for different sizes of the input. So if I have the language L prime that I talked about this morning, so it's all words where x is a prime. If I want to decide this language with a Turing machine, I can feed the Turing machine the word and it will tell me yes or no. But here, if I have a circuit, I cannot put in any number. I'm just restricted to 3. So I can just go from 0 to 7 in this case. Right. So here this is a main problem it's a main difference between circuits and Turing machines. So a circuit has a fixed input dimension. And how can we solve this problem? So we want now to talk about circuits, but arbitrarily long inputs, words that we want to put into the circuit. Yes?
Should we introduce a family of circuits where for each length, only one of the circuits will be used?
Yes, exactly. So let's, we have a family of circuits. Indexed by I, and this is the length of the input. So if I want to answer the question whether some word is in the language, and I come up with the circuits to solve me this question, I will use the circuit that has this length and give as input the word. And it will tell me yes or no. Or yes with some probability or no with some probability. But this is not enough. Well, in the morning we have seen, we didn't really prove it, but we have seen the halting problem, right? That there are some problems where a Turing machine cannot solve. There's no Turing machine that can decide this language. For instance, the halting problem. If you now have a family of circuits, we could solve the halting problem, because if you fix the input to 10 bits, let's say, we know kind of what we can just enumerate. We have, it's just a fixed size of input. So we could solve the halting problem with this. But the problem is that we want these circuits to be generated by an algorithm. And this is called uniform circuit family. So the idea is, you have an algorithm that generates Ci. And having that, we can now define the complexity classes in quantum computing. Or before doing that, let's get maybe some more intuition on how to compute with a quantum computer. So the idea is we have, let's say we want to solve decision problems, as we did also this morning. And we want to answer whether some word is in a language. So first, we run a classical algorithm, a Turing machine, M gives us a quantum circuit. C Turing machine M on input, on input, the length of this word. This is a quantum circuit CW. And a number n. You will see why. Then we run this quantum algorithm, the quantum circuit, on the input, written in the computational basis. So this is the computational basis. But if I have a bit string, then what I mean is 0, tensor 1, tensor 1, tensor 0. Okay. So we run this circuit, on that input tensor some zeros, because maybe the circuit, or no, we can actually forget about it. That's fine. Sorry for that confusion. But now, after running this, the circuit with this input, we might we end up with a quantum state, but we want to answer a question, a decision problem, so we have to measure. And we measure the first qubit of the output. And then the measurement result will tell us something about what we want to compute. Okay, so this is the general idea. So we can now define BQP. So this is bounded error quantum polynomial time. So this complexity class is the set of all languages, so of all decision problems, where there exists a Turing machine M such that for all x, if we give the input to M, this Turing machine M runs in time polynomial and outputs a quantum circuit. Q over Hadamard T and C naught. So this Turing machine takes the input a length of a word and outputs a quantum circuit that is composed out of these gates, Hadamard, T and C naught. Where if x is in the language, then probability that the quantum circuit, by doing the measurement at the end, will output 1 is larger or equal than 2/3. If x is not in the language, then this probability expression is smaller or equal to 1/3. So we have a Turing machine M that takes the length and outputs a Q, and then we use this Q as a circuit, give the word into Q, and we measure. This is how I denote the measurements, the first system. So this is only 1, and if these are n systems, then this is n minus 1. We don't care about this, we just measure this. If we measure 1, then we accept. If we measure 0, then we reject. So, and this probability expression what do I mean by that is the measurement operators I choose now are these, where there have I just care about the first system of the output. So this is the measurement operator, and I don't care about the remaining systems. So here we see the condition for measurement operators is satisfied. Right. Is this okay? So I run the circuit U on X. I'm sorry, actually you really need some, because this is just composed out of C naught, T, and Hadamard, so this is a unitary. The whole thing, Q, is a unitary operator, but I might need some extra qubits. So let's say I have some m qubits in the state 0. So this is having the input state, X tensor 0, evolving it with UQ, the unitary that is implemented by this circuit Q, and then measuring the operator M1. And this is the probability of getting 1 at the end. So a language is in BQP if there exists a Turing machine that, given the input of the length of a word, it outputs a circuit. And if I run this circuit with the word as input, if X is in the language, then if I run the circuit with the word as input, I get 1 with probability 2/3 or more. And if X is not in the language, then if I run the circuit, I'll get 1 with probability 1/3 or less. This is how we can define the class of languages that are efficiently decidable by quantum computers. Okay?
Amin?
Yes?
So to define BQP, is it enough that the Turing machine runs, the classical Turing machine runs in polynomial time? Or should you also assume that the circuit it produces has only polynomial number of gates?
Yeah, so this circuit, the classical one, outputs the circuit, but it's actually it's a description of a circuit. So it cannot be longer than polynomial. So the number of gates that appear in the circuit are also bounded by polynomial. So what is an example of a problem a decision problem that is in this class? One example, and I think the most famous one, is factoring numbers. So today in the morning, you have seen the decision problem for factoring numbers. So I give you a pair of numbers, and the question is, does there exist a prime factor for the first in the pair that is smaller than the second in the pair? This was and if you can solve that decision problem, we can find the prime factors of a number. And there's this famous algorithm for quantum computers. It's called Shor's algorithm. that does this, and so we have actually I think I called it fact for factor. This language is an element of BQP. But of course, it's a big question whether it is in BPP. You don't know. And all of, not all, but a lot of cryptography is based on that, right? That we cannot factor efficiently, or we think we cannot factor efficiently, but with a quantum computer we could factor efficiently. All right. Now we define another class. It's called QMA. And QMA stands for Quantum Merlin Arthur. And this class is the quantum analog to NP in the classical case. So it contains all languages for which there exists a Turing machine M such that for all x, if you give again the length of x to this classical Turing machine, this runs in time in polynomial of the length of x. And outputs a quantum circuit Q, again over the same set of gates, T, H, and C naught. And if x is in the language, then there exists a quantum state such that if you run this circuit with x and that quantum state, the probability of getting 1 at the end is larger or equal than 2/3. And if x is not in the language, then for any choice of quantum state, the quantum circuit will output 1 with probability 1/3 or less. So you see kind of the analog to NP that we defined this morning. We said that a language is in NP if there exists a polynomial time verifier, and if x is in L, then there exists a witness, and I can run this polynomial verifier to check the solution. If x is not in L, then any witness or any choice will tell me, no, it's not a correct solution. Here's the same thing, but instead, the witnesses can be a quantum state. And we have probabilities because we do measurements at the end. So if you would draw this now as a picture, like we did here, you have again a classical Turing machine that takes the length of the input and outputs the circuit, and this is the circuit. But now we say there exists, if x is in L, then there exists some quantum state, and then I have to put in zeros at the end. So if it is in the language and there exists such a quantum state, I can put into the circuit, and it will output 1 with some probability. And here, this probability expression is just very similar to what we have seen before. So Q of x get phi equal 1. This is trace. So we do a measurement with a measurement operator M1. Then we have the unitary that is implemented by the circuit Q. We have the input to the problem, the witness, and some zeros. Given like this. All right, do you have questions so far? So, if not, we can think about where are these classes with respect to the classical ones that we defined. So before we have seen these relations with the classical class P, BPP, P space. So where do I have to put BQP and QMA? First, what is the relation between these two? Exactly. Why?
Because here we have an added resource of the certificate.
So
if you don't have a certificate here, this like
we can just solve it. Yes, exactly. Here we have this additional. If x is in L, then there exists a state that's such that this is 1 probably 2/3 or more. But in BQP, we don't care. You don't need a certificate. Okay, and what about the relation to other classes, to the classical ones?
I mean, P would obviously be contained in both, and then BPP
Yes.
also be contained in BPP, I think.
Yes?
Because I mean, both of them are probabilistic. One has more, can do quantum stuff.
Exactly. So we can simulate classical computation on a quantum computer. It's just a special case. And there is probabilistic. So we have this. And then we said we have BQP is contained in QMA. And it's also known that QMA is contained in PP. Okay. So what does this tell us? of course, a big question is now the relation between dqp and np. This we don't know, just similar to p and np. But this question is more interesting if after I give you this following assumption. It's called the NP hardness assumption. Let me just move for that. And this assumption states that NP complete. So what does NP complete mean? This means that these are the hardest problems in NP. And if you can solve that problem, like we had seen in the morning 3 set was such an example, satisfiability of logical expressions. If that could be solved efficiently, then every decision problem in NP could be solved efficiently. So this is what the completeness means of a problem. So this assumption says that NP complete problems are intractable in the physical world. And this assumption was formulated by Scott Aronson. And the reference, if you want to read about this, it's called NP Complete Problems. And physical reality. And it appeared on the journal SIG ACT, SIGACT News 2013. Okay. So what does this NP hardness assumption say? If we have you can read it in the following way. If you have a model of computation, like quantum computing as a model of computation, and that model could solve NP complete problems efficiently, then this NP hardness assumption would say that this model is not physical, right? Maybe a bit more concrete. Where is it? So more concrete, if we first take a theory, let's say take a theory T, like quantum theory, but it can be any other theory. Then we define a model of computation based on T. So this means we build a computer with that theory, and then we study the computational power Now, if we find that the bounded error theory T kind of model of computation probabilistic time, if this class contains NP, then according to that assumption, T is not a physical theory. It's a very strong statement, but what it does, it gives us, the NP-hardness assumption gives us a tool from computer science to study physics, whether something is physical or not.
What does not a physical theory mean?
Yes, good question. Kind of, we cannot, what this machine does, we cannot build it in an experiment. We cannot.
In our universe?
Yes.
Or in any conceivable universe?
No, we cannot realize it. Yes. We cannot do an experiment and then actually solve these decision problems in these times that the model will tell us. Yes. But it's an assumption, of course. We don't know. It's called the NP, and we will never know.
We could say a conjecture more than an assumption?
Yeah, we can say it's. No, I don't. This is to be discussed, I think. It gives us a tool to test theories and like whether they are realizable or not, in principle. But what is this based on? So why should we buy this assumption or conjecture? Maybe it's better to, I don't know. I think the more you buy it, the more you call it conjecture than assumption. But why should we? Why should we? Do you like this at all? Maybe you don't like it. Maybe you completely disagree with this view. If not, I will be interested why. If yes, I'm also interested why.
No, I believe I read the article.
Yes? Okay. Okay, because it's Scott Aronson. Because
No.
Okay. Yes.
So is this the other way around as well? For example, if T is not a physical theory, then BTB contains NP.
No.
So the case is also.
No. Can we come up with a dummy theory that is extremely bad in computation, but we cannot think of it as being physical?
So for example, if you take a non-local resource, if you define class for non-locality,
Yes.
can we say something like this, that the complexity class corresponding to non-locality is subsumes NP?
But then we need to connect non-locality with computation. So the model of computation will be have non-locality as a resource, just like PR boxes, and then do computation, and we cannot.
So are there any classes defined based on that?
Yes, there are classes defined on. It's called box work, where we can have non-locality. Or there are classes defined on like a generalization of quantum theory. So in quantum theory, the quantum system is actually quite new result from this year or last year. A qubit as a density operator, I didn't write this down, but now it comes, can be written in the block representation as in the following way: 1/2 plus alpha x sigma x plus alpha y sigma y plus alpha z sigma z, where sigma y, sigma x, sigma y, sigma z are orthonormal bases for 2x2 matrices, the Pauli matrices, and alpha x, alpha y, alpha z are coefficients. So a quantum state, a qubit, can be represented as a vector in a three-dimensional ball, where these are the direction of the vector. So where's the... And on the poles, we have the states 0 and 1. And on the surface of the ball, we have all pure states. And in the center, we have the maximally mixed state. And here we have all mixed states. But on the surface, we have the pure states. But now we can think of a generalization of this to higher dimensions. So this is a three-dimensional ball. The quantum system as a density operator is given by a vector in a three-dimensional unit ball. You can go to higher dimensional or smaller dimension. You can think about two-dimensional or five-dimensional. But with some assumptions, reasonable assumptions, one can show that the model of computation that results from this cannot even solve problems in P. So it's extremely weak. Yes, you cannot do, and you have non-locality, but you cannot do anything interesting. Yes.
But the non-local model would be not a useful model to try to link with computational resource, right? It would be more like, hey, let's assume we have an oracle to the Hawking problem, and what can we do with that? So wouldn't a more reasonable question here would be we have an oracle for some bigger complexity class, and what can we do now while our standard Turing machine has access to that other bigger oracle?
Yes.
Right? So, for example, this standard model would be, hey, I have access to the oracle for the Turing for the Hawking problem. What can I do with it?
Exactly.
I can go one step up in the undecidability layer.
Yeah.
So what if, so going back to the NP-hardness assumption, what if P versus NP is undecidable? What would that have as a consequence for the assumption?
Well, the assumption is not.
Would it be valid to even state, like, to have this assumption if we can prove that P versus NP is undecidable?
Yes, yes, because it does not relate on the. Well, it relies on the assumption that P is different from NP as well. I mean.
But if it's undecidable, I'm saying.
If it's undecidable, no, this is kind of a part of this assumption that P is different from NP, right? Because we know we can build Turing machines.
But it's kind of referring to this physical world, right? Which the standard P versus NP question doesn't ask. And that's, I think, partially Scott's motivation to kind of connect it with, not worry about the general mathematical question and have it connected to the physical reality, just like with the Church-Turing thesis versus general mathematical thesis, but then you have kind of the physical version of the Church-Turing thesis.
Yes.
Right. So over here, then, if you kind of take the mathematical question of P versus NP and say, hey, let's say tomorrow we can prove that it's undecidable, would it still be reasonable to state this assumption and say, hey, we can still use this assumption?
No, but then this assumption will be violated.
I don't know. Is it because we are saying that mathematically we can't answer P versus NP? It doesn't necessarily.
Yes, but we think Turing machines are physically realizable. If P is equal NP, then.
No, but I'm saying we find out that P versus NP is undecidable. So we don't
Yes.
know
Yes.
whether they're equal or not, and we find out that we can't give a mathematical either way. What would this assumption constitute at that point?
I see your question.
Like, does the mathematical result have a consequence for this physical reality assumption?
I don't know. Yes. But if you would prove P equal NP, then we have to get rid of this assumption.
Right. Yeah.
Yes. Yes. But the other way, yes.
Well, I'm not saying equal or not equal, right? I'm going kind of the third option.
Yes. Exactly. Yeah. It's. I don't know. But so what are the. Yes, so this is something highly debatable, I think. And it's good that we talk about it. But one way maybe to see this, why we might dare to put such an assumption at all, is that people have come up through the years with new models of computation, and they try to solve NP-complete problems efficiently with different models of computation. And they went to the lab and tried it, and it always failed. There was always a problem. And the history sounds very similar to all these attempts to have communication faster than light. So we can also maybe put this assumption based on experience that we did not manage to do that. And there was always something small that was problematic. It's kind of always avoiding us. And of course, another motivation why we, at least for the importance to discuss this, was Gödel already noted that. And he said that if you could solve NP, if NP complete problems would be tractable, then the mental effort of a mathematician for yes or no questions could be completely replaced by a machine. So I think this would have huge philosophical and practical implications for all of society. So this is kind of the reasons that one gives for this assumption to keep it. And the nice thing is it gives us a tool. Unless if it's undecidable, one has to think about it. Yes. Okay, I have some more minutes, huh? Yes. So, having this NP-hardness assumption, now we can look at BQP, which is the class of tractable problems with a quantum computer. And, well, this is an open problem, of course. The BQP, how BQP relates to NP. We don't know. So if NP would be contained in BQP, then according to this assumption, quantum computers are not, we cannot build them. They will, when we try to build them at some point, we will fail. We cannot go to big systems. But most people conjecture that NP is not contained in BQP, so that we cannot solve NP-complete problems with a quantum computer. So, for tomorrow, we will then talk about causality. This will be the main topic tomorrow. So we'll talk about what do we understand as causality and causal structures, and we will modify these definitions of causality, and then we will do exactly this program what we did now for quantum computers. We build a computer based on a modification of the definition of causality and study the computational power and try to say, with the help of this assumption, whether this modification on causality makes sense or not. But I will not be able to get into that today because we just have no time left. But I want to give you a list of topics that I did not mention. And if you're interested in quantum computing and quantum information, you definitely should look up these topics because that's very interesting things. So there's a Shor algorithm. So I'll just give you a list of interesting things. So the Shor algorithm is the algorithm that factorizes numbers into prime factors efficiently with a quantum computer. Then there's Grover's algorithm, or Grover's search. This helps to find an element in a database, unstructured database, with a quadratic speedup compared to classical algorithms. Then quantum cryptography. This is especially something called BB84. This is something very interesting, I think. And this is the most practical, I would say, what happened throughout the years. So there are companies that sell quantum cryptographic devices. And Bell non-local correlations. So I can definitely recommend you these topics, and maybe Fabio or someone else has some more ideas to share. No. There's a lot of things. There are a lot of things. And yeah, many of them are also in this book. So if you're interested, you can always just ask me for the book and you can have a look at the book.